Good afternoon to everyone.
Very good afternoon, sir. It's good evening now, I think.
And apart from this, some more people are expected to join. So let them join, then we can start within a couple of minutes. Now all have joined. All have joined. IT, electrical, Mayur Shukla sir, Vandana Vaishnav, Sonia madam, Chike, Sonia Gupta sir, IT, all have joined. Now let us start. Rupali madam and one or two are left. Director madam will join in between, I think so.
So, sir, shall I start?
Sunen sir, what do you say? Is it to be started? Sunen?
Yes, sir. Yes, sir. Yes, sir.
Okay, now let us start. Okay, carry on, madam.
Okay, very good evening to all. I think today is the 5th day of presentation peer review program. So the topic of my presentation is miniaturization and integration of antenna and filter for radio frequency interference. It is integration of microstrip antenna and microstrip filters for radio frequency interference. The topics which I am going to cover, these are the contents. Before moving ahead, I think you all must know about the radio frequencies. As I am talking about the radio frequency interference, microwaves, actually these are the microwaves having very high frequency range from 300 megahertz to 300 gigahertz. And as per IEEE standards, the various bands are defined for these frequencies. And my work is particularly on these three frequency bands, L band, S band, and C band. L band frequency range is from 1 to 2 gigahertz. S band frequency range is from 2 to 4 gigahertz, and C band is from 4 to 8 gigahertz. L band frequency range 1 to 2 gigahertz when we are saying, and the GPS application, for GPS application, the frequency required is 1.6 gigahertz. So it comes under L band. And S band 2.4 gigahertz, जो कि अपने राउटर में अवेलेबल होती है 2.4 gigahertz for WLAN WiMAX applications. 2.4 and 5.2 gigahertz comes under C band. So my work is basically on these three frequencies, 1.6, 2.4 and 5.2 gigahertz frequencies. I worked on these three frequencies. As I am saying, it is the integration of microstrip antenna and microstrip filters. So before moving ahead, you also must know about the microstrip patch. What is this microstrip patch? It is a substrate of 3 layers. The lower one is the ground plane, middle one is the dielectric material, and upper one is the conducting plane. So it is made up of 3 layers: ground plane, dielectric material, and the conducting plane. So I designed the microstrip antenna and filter on this microstrip substrate, and the topic is miniaturization and integration of antenna and filter to reduce the radio frequency interference. So I designed both antenna and filter on this microstrip substrate. So as we know that miniaturization, low cost and good efficiency are the basic demand in today's printed circuit board technology. And size reduction has been a trend in wireless systems design. So due to increase in demand of wireless services, the channel interference is increasing day by day. So it is necessary that the device cover their allocated spectrum efficiently. And the user demand is to use all these technologies in as small devices as possible. So keeping in view all these points, I choose my topic as miniaturization and integration of antenna and filter. So now the point arises, why integration of antenna and filter? Actually, antenna and filter are considered as the critical component in reducing the whole size of the radio RF front end design. Actually, RF front end design, actually it is the part of a receiver side of either mobile, laptop, किसी भी चीज की बात करें तो रिसीवर साइड जो होता है ना, that consists of RF front end. First The first element is the antenna that receives signals, then filter, then low noise amplifier, mixers, many components are there, but antenna and filter are considered as the critical component in reducing the whole size of the RF front end. So integration of antenna and filter is a topic of great interest, which provides both the filtering as well as the radiating function. So the integration, generally antenna and filter are connected through a waveguide. So it takes a lot of space. So my topic is the integration of antenna and filter on a common ground plane. So the term filtina, it comes from the integration of antenna and filter. The integration of antenna and filter on a common ground plane is known as filtina. So many structures, filtina structures have already designed. So this is the monopole rectangular antenna integrated with a bandpass filter design for a single frequency application. Here the microstrip rectangular patch antenna is integrated with a hairpin type bandpass filter, again for a single frequency application. Here the circular monopole loop antenna is integrated with bandpass filter. So basically the integration of antenna and filter is there, and it is known as filtina. As I said, the microstrip substrate consists of a ground plane. So here I am trying to integrate antenna and filter on a common ground plane. So this is the literature review of my work. Actually, previously so many filtinas have already designed, but that design were based on the single frequency or dual frequency applications only. Okay, this is my work. I published in 2017. This is a rectangular microstrip patch antenna on the top layer, conducting plane, and this is the bottom layer, the ground plane. I introduced a defect in the ground plane, and 4 surface mount capacitors I placed here. So, and at the center of this dumbbell shape, I introduced a pin diode. Incorporated a pin diode in between these two dumbbell shapes, this dumbbell structure. When the diode is in forward bias state, it will give the frequency of 5.6 gigahertz. And when the diode is in reverse bias condition, the frequency switch from 5.6 to 2.45 and 5 gigahertz. So it is a reconfigurable structure capable of reconfigure the frequency band from one frequency to another frequency just by switching of the diode. So this is the work I did in Center for Applied Research in Electronics under the supervision of Professor S.K. Kaul, IEEE Chairman of India. Now the work which has already been done previously, it has some limitations. Various antenna filter integrations have a very large size due to improper utilization of substrate space. Matlab integration of antenna and filter previously has already been done, but they were using a very large size of substrate material. Few dual band filtering antennas have been proposed by many researchers, but no work has been done so far for triple band filtering antenna. As I said, my working frequencies were for L band, S band and C band. So I was trying to integrate triple band antenna with a triple band bandpass filter. So previously so many work has already been done, but it was only for the dual frequency band. Dual band antenna and filter integration has been reported in the past, but triple band antenna and dual band integration is not reported. So my objective of designing was to design and characterize the novel triple frequency band compact antenna for WLAN WiMAX applications. I designed a compact size triple frequency band application for triple frequency band application and antenna, small antenna. And to design and characterize band pass filter for WLAN WiMAX application, then to integrate antenna, that triple band antenna and filter on a common ground plane for size reduction. And then I introduce reconfigurability in filtina structure. That is, integration of antenna and filter is filtina to achieve multi-band structures. So these were my objectives. Research methodology I applied. First of all, the problem identification, then tool design, tool required for designing of this antenna structures. This is CST, computer simulation tool, and many other tools like HFSS and Microstripe 7 are available. I worked on CST, computer simulation tool. I used the Shiv Nadar University. It is available, licensed software, CST software is there. Then designing, simulation and optimization of the proposed antenna. After that, I fabricated the antenna in IIT lab, Center for Applied Research in Electronics. Then characterization and measurement of network analyzer, and comparison of the simulated result, simulator output with the output of the network analyzer after fabrication. Comparison of the two. If the results are satisfactory, I went for publication process of my work. So the first design, as I said, I designed a novel triple band antenna, which were capable of to work in 3 different frequency band: L band, S band, and C band. So my process started. I designed as the 3 frequencies I decided: 1.6, 2.4, and 5.2 gigahertz. The highest frequency was 5.2 gigahertz. For WiMAX applications, Wi-Fi communication के लिए 5.2 gigahertz था. So as we move towards higher frequencies, the size of antenna reduces. So I choose the size of the antenna, which is the smallest size, at 5.2 gigahertz. So many formulas and analysis work is there to find out the exact dimensions of the length and width of the antenna. It is given in Balani's antenna designing book. So I choose the dimensions for 5.2 gigahertz frequency band. The length is 22 mm and the width is 20 mm. First of all, I designed a simple rectangular patch antenna for 5.2 gigahertz frequency band. Then I introduced a rectangular split ring resonator inside its slot. As I introduce a slot inside the rectangular patch, it divides the current into 2 parts. So we get 2 frequencies in this. And after that, I introduces a small defect of 5 mm cross 2 mm in a ground plane. It's a partial ground plane. जो हम ground plane की बात कर रहे थे, it's a ground plane, then dielectric material, and then conducting plane. So this rectangular patch I etched on a conducting plane, and this is the ground plane. Etching is there, and the only left length is 9 mm cross 25 mm in the ground plane. So when I designed this structure, this is the rectangular patch antenna which gives the frequency 5.2 gigahertz. So I introduced this split ring slot inside this rectangular patch antenna, and a defect in the ground plane just behind the feeding line of the antenna of 5 cross 2 mm in back side of this antenna, and the partial ground plane is there. When I introduced all these defects in actual 5.2 gigahertz design, at that time I found that my desired frequencies were 1.